Good morning and welcome to our webinar. This is a 10th webinar from the series of breakfasts with MSA, and the third one where we are comparing the ISO and MSA approaches to the overall evaluation of the measurement device capability. And now, in this third one, we'll concentrate on the measurement process. All right, it seems we gave a time for just about everyone to join. So let's get rolling. Very well, so similar to what I've said the last time about the measurement system, the main difference between the ISO and MSA approaches is that MSA tries to find out individual criteria for all the individual uncertainties that we have, while the ISO is trying to combine them and find out an overall criteria for this combination. And as you can imagine, there is not a one-to-one comparison between these two. So they cannot match directly, and none of those two approaches is perfect. They both have pros and cons. So it is good to know what is the difference in between them. So let's see how the ISO works. This is for the ISO. I have here again the formula for the combined standard uncertainty, combined and standard uncertainty for the measurement process. It is a square root of sum of squares of all the uncertainties that we have, with the exception that in this place we need to have the uncertainty of the repeatability. And as I've said, nothing is perfect. So here, this part of this equation is trying to eliminate the correlation between the uncertainty between the repeatability, uncertainty of repeatability on the reference, which is part of the measuring system, and on an object, which is part of the measuring process. And moreover, in devices that have very low uncertainty from repeatability, this may also be a result of the resolution. So this is trying to combine those. And the overall criteria is that we take 4 times the standard uncertainty divided by tolerance, and this has to be less than 30%. In other words, plus minus 2 standard uncertainties, that is 4, needs to be less than 30% of the tolerance. So this is the ISO way, and quite a good one, I would say. And on the MSA, on the AIAG MSA side, That is a special quantity with a special criteria, similar to CG/CGK we had the last time. Here we have the famous gauge RNR, GRR, standing for gauge repeatability and reproducibility. The formula for the overall evaluation is very similar. The GRR, just a reminder from one of the past webinars, it tries to decompose the overall variation it sees in the measurement process experiment, and then take out the part variation and leave everything else in. And what stays in is the main influence, which is the main factor, which is usually the appraiser, the operator, the repeatability of an object, which is something which is not explained by the general formula, and possibly the interaction, meaning the interaction between the main influence, possibly the operator, and the measured part. This interaction plus the main influence is the reproducibility. So we have that. It is again a square root of sum of squares. And we treat it in a very similar way with two exceptions. Instead of 4, we have here 6. And instead of 30%, we only have here 10%. So this is extremely strict, much stricter than the original formula. This 6 is plus minus 3 standard uncertainties. That's because this is probably historically coming from the side of the production processes, where we require 99.73% confidence being intolerant, which leads to this plus minus 3 standard deviations. So it's just translation of that. And 10% is just being conservative. So how do these two compare? If we reformulate what I have just said, we can state what is the GRR in terms of percent of tolerance. If we just divide the 10% by 6, we get 1.7% of tolerances. And on the other end, we divide the 30% by 4, and we get 7.5. Of course, unlike in the measurement system, where I've been working with the bias and repeatability, this is a multi-dimensional problem, multi-dimensional issue. But anyway, the square root of squares is a formula for a circle, or with 2 components, and a sphere with 3 components, and a sphere in a multi-dimensional space for 4 and more components. So basically, it's just a spherical surface. It is really spherical. It's not an ellipse, as with the measurement system. So I have decided to divide it into 2 components. One is the gauge RNR down here, and then the rest. And everything else, the rest is up here. So with the gauge RNR, we have just one tolerance, one limit on the horizontal axis, and that's the 1.7 if we speak in terms of percent tolerance. And if we are below that, we are fine. If we are above that, that's non-conformant. And with the ISO, we have the circle. If we are inside of that circle, this is a quarter of a circle because, of course, we can't have negative standard deviations and standard uncertainties. If we are inside of that, we are okay. If we are outside of the circle, that is not okay. And of course, you can see already there are two regions where this does not agree. The good thing is that we have two regions, not just one. If instead of this 1.7, if this would move beyond this 7.5, that would be a worse situation. And again, this is not just a theoretical idea, theoretical reasoning. This really can happen, this disagreement. And I would like to ask Martin to show you how you can find that out in Yarvin.
Good morning for everybody. So for this showcase, I have prepared some example with standard quantities of positioning and geometric quantities. We have runouts, parallelism, diameters, and so on. We have all necessary information we need for the evaluation. We have specification limits. We have some master for the evaluation, and we can do the we can go to the results. But what's important in here is for the experiment type 2, for the measurement process, we need to choose what's the main factor. The main factor is important. In this case is reproducibility of the measuring system. And this is telling us for what factor will the ANOVA, the analysis of variance, will be calculated. And we chose this one because in this experiment, we compare two different machines, 3D machines from two different vendors. So we have all the data in the experiment. You can see it's standard experiments with 10 parts, 2 levels. It means I have two 3D machines and 2 repetitions. And we have the table with the results. The results was imported through DFQ files. And so this is our experiment. And in the next step is B-type uncertainties. We have some B-types in here. We have inhomogeneity of object, of measured part. And we have uncertainty from temperature. So this is the experiment, how it is defined. Some information was measured, some information was added later as B-type uncertainties. And if we go to the result, I will this way. And what's important for us right now are those 2 characteristics. The first one, MSA and OK, ISO OK. If we can look closer to the results, you can see that QMP, the result from ISO and from VDA5, is about 16.5%, and gauge RNR is a little bit more than 22. And the common use criteria for gauge RNR is saying if it's more than 10 or sometimes 20%, it means that the measurement system is conditionally capable and it should be reviewed. It cannot be used as it is okay. 22% is a little bit too much, so it should be reviewed. Second example is the other one. I have GRAR less than 10%, and QNP is more than 37. So this is quite interesting, because according to one standard, it is saying no way, the measurement process isn't so good, so you should not use it. But other standard is saying, okay, your measurement process is fine. It even meets the strictest criteria that is in the MSA, the 10%, that is really strict criteria. So what's happened here? According to one standard, is way over the limits, and the second standard is saying your measurement process is completely fine. So what's happened? If we go to the details and we look to the uncertainties that was calculated, we can see what's happening. Because if we are speaking about the MSA, it means only the A-type uncertainties are in the MSA results. So, and not all of them. To gauge RNR, what here is the 22%, we have going just repeatability on workpiece, and reproducibility over measurement system, and interactions. These only three components are going to the gauge RNR results. And in this case, those components are too big. So that's the reason why gauge RNR is out of the limits. But the other ones that are calculated with the QMP, by the way, to the QMP, all of the components are calculated to the QMP. It means that it's not so big, because in here we have all the information. And if we look to the other one, where MSA is, according MSA, it's okay, and according the ISO, it's an okay, it's the same story here. We have the A-type uncertainties. In here, in this case, it's repeatability on master, it's reproducibility and the interaction. And you can see it's very small with the comparison of the other components we have, calibration, bias, object, and so on. So this is the reason why in this case, according to MSA, the results are fine, and according to ISO, the results are out of the limits. And the reason is, by general, we can say to the gauge RNR, only some of the components are calculated, instead of ISO, where are calculated all of them to the results. So this is from me, and now we can go back to Jaroslav.
Thank you. So let's try to analyze from the inside what is going on here. The explanation needs some assumptions, as we are in a multidimensional space here, and we only can reasonably speak about 2 dimensions. So let's try to break it down. The gauge RNR here is pretty strict, below 1.7% of tolerance, all right, above, not okay. And this is not really, and the ISO gives much more space here, up to 7.5%. On the other hand, everything what is up here, the other parts of the measurement process, which actually includes the measurement system, the gauge RNR doesn't care about. This is being taken care of by the CGK. So up here, it can go to whatever level. The GRR does not care. The ISO, on the other hand, is trying to put limit on everything, on the combination. So it is really expected that it will first limit something what is up here, so it cannot go to whatever high number. But also, since this is a combination, the ISO, or the VDA5, will allow some span in this direction. And this is the nice thing about the combination. The overall uncertainty of the measuring device is the thing that matters, is the thing that, let's say, it spoils our measurement. And if we are ready to allow certain level of this uncertainty, then it is only natural that we'll, if some component of the measuring process is very precise, we can allow the other parts to go further than if they would be evaluated individually. It's if the repeatability is very good in individual appraisers, then we can allow a little higher variation in between the appraisers. Or if the device is very robust to the change in the temperature, then we can allow a little wider range for the repeatability. And that's the reason why the limits in the ISO part are actually changing from the individual points of view. If the gauge RNR component is high, let's say up to here, there is a limit on everything else in this direction. So if one component takes the space, it limits the space for the others. And that would be the analytical explanation of this circle or a sphere. And now let's see approximately how this works in terms of the size of the components. Which of these are big usually, which of these are little. So naturally, what is the main factor tends to be big. That's the reason why it is the main factor. Also, the repeatability on an object, this is a fair concern, should be, it usually is some non-negligible component of the overall uncertainty. On the other hand, the interaction, that's not really usual to see a big influence coming from an interaction. And from the side of the measuring system, we need to take a good care about the bias. That is a substantial component together with the linearity. That's really a bias, but looked at from slightly different perspective, as we spoke about that in one of the past webinars. And the measured object, which is greatly influenced by the definition of the measured parameter. And we'll speak about the importance of the definition of the measured parameter in one of the future webinars. On the other hand, the calibration should be negligible. Really, the stability of the measuring device, that's a more of a process thing. For how long we'll keep the measuring device unattended, unchecked, and it should be only so long so that it does not influence the overall results. Temperature, there is a question, there is no clear answer on that one. The rest is usually not used. If there is a good reason to use the rest uncertainty, it is probably influential. And the gauge variation, it is only in special cases. In most of the cases, we use just one measuring device, so there is not that problem of comparing several measuring devices, so the gauge variation in most cases does not play much overall. So you can see the substantial variations are really divided. They really are in both of these groups. So it really makes sense to limit the other if the one is, let's say too big. And also not to limit the first one if the other is small. So overall, I would say the ISO approach is better. This complex point of view is better. There are some compromises here and there, specifically on the correlation of on the individual uncertainties, but this is something we tried to deal with by taking out the repeatability. That's the biggest correlated influence. And overall, the ISO works, while the gauge RNR needs the other point of view, which we know is far from perfect from the past webinar. All right, we have. I thought we had a question, and I see it's already being answered by Martin. Very good. So thank you for your question, Vikas. And I think this is it for today. So thank you very much for your attention. Hope you had a fun in this series of 10 webinars. And we are indeed getting ready for the next series of 10 with lots of topics which have not been covered in the past webinars. The MSA is really a wide topic of endless possibilities for discussions. So I'm hoping you'll stay with us, and I'm looking forward to see you the next time.
Diribet, we are Diribet. Diribet, we are Diribet. Diribet, we are Diribet, we are Diribet.